Yesterday we did a little demonstration in class where we dropped a set of keys and a piece of paper, and I polled you ahead of time. I said, which ones are going to hit the ground first? I had a set of keys in one hand, I had a flat piece of paper in another hand, and almost everybody said the keys were going to hit the ground first. Okay, we all had in the back of our minds this intuitive notion of air resistance. Air resistance will cause the piece of paper to fall at a slower rate than the keys. But then I proceeded to crumple up the piece of paper, drop the crumpled up piece of paper along with the keys at the same time, and they hit the ground at the same time. The point of that demonstration was to tell you that in the absence of air resistance, when there is no air resistance, every object will fall at the same rate. And the rate at which they will fall is that 9.81 meters per second squared value that you learned about in Science 10. Now, is there ever truly no air resistance? No, there's always air resistance. One of my professors at university, though, once defined physics as the art of making the right approximation. So what he was saying there is that, look, physics is never 100% perfect. We're always approximating something. If we drop a brick from a building, there is air resistance, but we're approximating it as if there isn't air resistance. And you know what? That's a good approximation. For most things, it's a good enough approximation to assume there's no air resistance. There's exceptions to that. But for most things, we can say that. There is no air resistance. And therefore, they should fall at a rate of 9.81 meters per second squared. You notice when I uncover that and you see the number there, I've got a negative in front of that. Does anybody want to suggest to me why that might be a negative 9.81 as opposed to a positive 9.81? Yep. Okay, it's falling downward. All right. So it's accelerating, it's speeding up in the negative direction. What if I threw the keys up in the air, Nathan? Good, good. Not the pressure of gravity, but the force of gravity is still acting downwards. Good, excellent. So whether the object is falling or whether the object is rising up into the air, gravity will still be negative 9.81. An object that speeds up in the negative direction has a negative acceleration. An object that slows down in the positive direction has a negative acceleration. So any way you look at it, gravity is always going to be negative 9.81 meters per second squared. That whole idea of the negative acceleration doesn't just apply to gravity, although that's where we're kind of seeing it for the first time. In general, any time you have an acceleration, something speeding up in the negative direction will make it a negative acceleration, including gravity. Anytime you have an object slowing down in the positive direction, like an object rising but slowing down, then we say that's a negative acceleration as well. It doesn't apply just to gravity, it applies to other situations as well. But certainly in the context of what we're doing right now, it applies, gravity. The problems that we'll solve involving gravity are virtually identical to the problems that we've solved over the last several days. Look, it's an acceleration. If an object is accelerating downward because of gravity or decelerating upward because of gravity, it's a group B problem. All of those group B equations apply. When I look at this question, cliff diving in Mexico, a diver throws a smooth, round rock straight down with an initial speed of 4 meters per second. The rock takes 2.5 seconds to land. How high is the cliff? When I look at this question, the first thought that comes to my mind is, hey, this rock is accelerating. This rock is speeding up as it's falling downward. That's a group B problem. The only difference between this and the other group B problems that you have is that when you read between the lines, you see that the acceleration is negative 9.81 meters per second squared. So not only do we have the numbers that are given to us in the problem here, VI is negative 4. Why negative 4? Hey, why negative 4? It's thrown downward. So VI would be negative 4. The time, 2.5 seconds. In addition to those numbers that were given in the question, we know that the acceleration is also negative 9.81. Okay, that's the only thing that's different, the only thing that separates this question from the questions that you've been doing all week. Now we're looking for the height of the cliff. In other words, we're looking for the displacement of the rock, how far the rock falls during this time of 2.50 seconds. All right, how do we find out how high this cliff is? Well, we got VI, we got A, we got T. This is a problem we've done 1,000 times, right? Except the acceleration, the other 999 times wasn't 9.81. Now it is. We're going to say D is equal to VIT plus 1/2 AT squared. VI is negative 4. T is 2.5. A is negative 9.81. Don't forget these negatives, okay? It might seem like it's a small thing, but it's not. Okay, you have to include these negatives. It's really important. Times it by 2.50 seconds squared. Now, let's do this on our calculator to make sure that we can do it. Follow the steps that I follow in the way that I do them, okay? We're going to say negative 4 times 2.5. We're going to turn it on first. Then we're going to say negative 4 times 2.5. And we get a number that's negative 10. Write that number down. Write that number down. We're dealing with multiplication, addition, and we're dealing with some negatives in here. If you don't start doing it in steps, you try to do it all at once, you're bound to make a mistake somewhere with your calculator. So get that number, write it down. Plus, now, the second group of numbers here, 0.5 times neg 9.81 times 2.5 squared. Thank you. 2.5 squared. That gives me negative 30.656. So we've got negative 10 plus negative 30.65625 meters. Add those together, we're going to end up with negative 40.65625 meters, which I should round to our least precise or our weakest piece of data is 3 digits. So we should round this to 3 digits, negative 40.7 meters. Now, strictly speaking here, I haven't found the height of the cliff. What have I found? Nathan? Yeah. Even I haven't even really found the amount of the cliff that's above the water. Technically I found not even the height, right? Technically I found the displacement of the rock, right? How far did the rock fall? Well, why did I find how far the rock falls? Because that's the same magnitude as the height of the cliff, right? This is the height of the cliff. But we wouldn't say for the height of the cliff it's negative 40.7 meters. We'd say the height of the cliff is positive 40.7 meters. Now, if you made it if you gave me an answer of negative 40.7 for the height of the cliff, I'd mark that right. Okay, I'm not going to take off marks because you didn't drop the negative sign there. But just remember, technically, we found the displacement of the rock, not the height of the cliff. They just happen to be the same number, that's all. Comfortable with that? Is this really any different than what you've been doing for the last several days? Not at all. We just have something else given to us. We always have the acceleration given to us now, neg 9.81 meters per second squared. Try these 3 questions, please. See what you can do with those.